Perfect. Okay, so the next talk is about exploit generation across Node.js packages, and the presenter is Filipe Marques, and we are ahead of time, so you have even 10 seconds to breathe before starting.
Thank you so much for the presentation, Thomas. So hello everyone. My name is Filipe Marques, and today I'll be presenting our work on automated exploit generation for Node.js packages. This is actually joint work together with my colleagues at INESC-ID and CMU. So let me begin by introducing Node.js. Node.js is an open source runtime that runs JavaScript outside the browser. This makes it ideal for writing scalable server-side applications. And plus, Node.js is hugely popular. It ranked the most used web framework in the latest Stack Overflow developer survey. And it also plays a key role in modern full-stack architectures. And plus, it's been adopted widely across the industry. Node.js also has a rich package ecosystem. Its primary package manager, NPM, is the most widely used in the world. Currently, it hosts over 2.5 million packages. As a result, most Node.js applications today actually rely on these third-party packages. These packages, as a recent study highlights, a critical concern, these packages are often vulnerable. In fact, the GitHub advisory database has issued over 3,900 advisories affecting NPM packages. And these vulnerabilities can have serious consequences in practice. So over the years, we've actually seen several high-profile attacks targeting these NPM packages. And these cases highlight how one bad package can actually affect thousands of packages downstream. So, motivated by these risks, many tools have been developed to detect vulnerabilities in these NPM packages. And these tools have achieved some success. So many can actually detect a large portion of known vulnerabilities. However, they all suffer from the same fate. So they have high false positive rates. This means that developers are actually forced to manually inspect and triage each vulnerability to discard the false vulnerabilities. What this does is, over time, it leads to frustration and a loss of trust in these tools, ultimately resulting in poor adoption and, most importantly, many vulnerabilities remaining unfixed. And so, our goal is to improve the precision of these tools without sacrificing recall. So, to achieve this, our approach is to automatically generate a proof of concept exploit. So, by doing so, what we do is that we show that the vulnerability is both real and reproducible. This actually makes vulnerability reports more concrete and actionable, and actually helps developers quickly validate and also prioritize the issues. However, actually automatically generating this proof of concept exploits is difficult and comes with a major set of challenges. So the first challenge is that the exploit must actually invoke the function where the vulnerability actually lies. So current approaches only succeed when the vulnerable function is directly exported by an NPM package. But in many real-world cases, the vulnerable function is only reached after multiple interactions with the library. So here's an example illustrating this. The vulnerability is only called after the last method call. It's a pretty basic example with a trivial payload, but current tools cannot generate exploits for this. Secondly, scalability is crucial when dealing with many important packages. So current tools will either try to execute all the dependencies, which is often too expensive, or they simply ignored it. And both approaches have drawbacks. So either they have poor performance or missed vulnerabilities. Finally, current tools only focus on generating simple exploit payloads. So they don't support configuring payloads to fit specific patterns that may be required by the underlying code. So for example, consider a vulnerability where the payload must be injected inside a return statement that will be evaluated by the eval function in JavaScript. So actually, to succeed, the payload will need to be wrapped inside something like an anonymous function that will be executed immediately. Again, no existing tool can generate this type of exploit. And so, for these reasons, we've created Explode.js. Explode.js is a novel automated exploit generation tool that is capable of generating complex text drivers that can trigger vulnerabilities deep within a package. Explode.js also scales efficiently even when many important packages are involved. Plus, Explode.js is also able to compute these non-trivial payloads tailored to specific sensitive things. So currently, Explode.js only supports 4 types of vulnerabilities, path traversal, code injection, command injection, and also prototype pollution. And our evaluation demonstrates that Explode.js outperforms existing tools, generating 300% more exploits than fast, and also 500% more exploits than Node Fine. Explode.js has also discovered 44 new zero-day vulnerabilities, and these include 3 CVEs and 1 GitHub security advisory. Let me now walk you through the design of Explode.js. So we'll start with a motivating example. You can see the vulnerable package here on the right, or maybe your left, and the exploit over here. So actually, don't worry about understanding all the details of the vulnerable package. Let's just focus on the exploit and how it works. So the first thing the exploit does is it actually requires the vulnerable package. Then it creates a new instance of this file transfer class. It prepares some data, and then it defines this user object with a host property and also a specially crafted -dir property string. Finally, the code will execute this run method with our user object, which, due to improper sanitization, will flow into the exec function, which is actually a known vulnerable command injection function. So the payload that we injected to our -dir property string, which is passed by our user object, is actually a typical command injection payload. So it will actually attempt to create a file named success in the file system, which is actually a common technique used to signal that arbitrary command injection has been achieved. And moving on to the architecture, the way that Explode.js generates these types of exploits is actually through a 2-stage pipeline. So the first stage is the exploit template generator. It essentially starts by taking an npm package and produces these symbolic exploit templates that will serve as the starting point for exploit generation. And then in the second stage is the exploit template resolver, and we try to find the concrete values, such as the concrete payload and also function inputs that make the template fully executable and try to trigger the vulnerability. So we start in the exploit template generator, and its first goal is actually to automatically determine how to interact with an npm package. So the output of this stage will be called a vulnerable interaction scheme, or for short, VIS. And as shown on the slide, a vulnerable interaction scheme is essentially a chain of function calls along with the required argument types that sets up the conditions necessary to trigger the vulnerability. With the VIS, we can now compile it into an exploit template. And essentially, an exploit template is an executable symbolic test where the inputs to the functions are symbolic values. And its purpose will be to drive a symbolic execution engine to explore the program and discover how we can trigger the vulnerability. If you see, this actually solves our first challenge in generating a test that can actually try to reach the vulnerability. So that brings us to stage 2, the exploit template resolver. So in this stage, we will begin by performing lazy symbolic execution of the templates we've created previously. So actually, the lazy symbolic execution is what will allow us to perform the exploration of the paths without actually running any of the third-party code. So crucially, this will avoid missing potential vulnerability and allows our analysis to scale. which consequently solves our second challenge, which is the scalability in the presence of many imported packages. So finally, when the execution path successfully reaches a vulnerable sink, symbolic execution will produce something that we call a symbolic outcome. And a symbolic outcome summarizes the detected vulnerability by telling us three things. So the sink that we reached, the conditions that were necessary to reach it, or simply the path that was taken, and actually the symbolic inputs that trigger the vulnerability. Using this symbolic outcome, we can now create an SMT query, and this SMT query is responsible by encoding the path constraints needed to actually reach the vulnerable code, and also the constraints that will ensure the well-formed-ness of our payload. So this is actually a very simple example where the symbolic input that reached the exact function with unsanitized inputs. So we can simply sequence an attack to the current command and ensure that it is well-formed. So while this attack actually uses straightforward attack pattern, Explode.js is parameterized to actually allow for writing more sophisticated attack patterns. And consequently, this actually allows us to solve the third challenge that we presented. Finally, we then pass this SMT query into an SMT solver, which, if it is satisfiable, will return a satisfying assignment. So, using this assignment, we can now instantiate the symbolic, the exploit template into a fully concrete exploit. To this end, in the exploit template, we simply need to replace the symbolic values with the concrete values from the model. And lastly, what we need to do is actually execute the concrete exploit and observe the intended side effects. So in this case, what this means is, for this type of exploit, we simply verify that a file named success was actually created in the current file system. So let's now look at how Explode.js actually performs in practice. So we evaluated Explode.js with respect to 4 main research questions, but in this presentation, I will only focus on the first 2. So how effective is Explode.js at generating exploits? And can Explode.js find zero-day vulnerabilities in real-world NPM packages? So to evaluate Explode.js, we actually used 2 well-established vulnerability datasets that were actually used to evaluate previous related work. So we used Vulkan and Secbench. And because these datasets actually contain real-world CVEs, they provide a representative and also realistic benchmark for assessing these automated exploit generation tools. So when evaluating effectiveness on the ground truth datasets, we show our recall and also our exploit rate. And when inspecting each of the vulnerability categories, we see that Explode.js consistently outperforms existing tools across every vulnerability category. And overall, Explode.js generated exploit for 46% of the vulnerabilities in the dataset, which is 4 times the exploit generated by FAST, and also 6 times the exploit generated by Nodemedic. Then, we actually ran Explode.js on a dataset comprising of 32,000 popular NPM packages, and we started out by detecting 291 symbolic paths that reached the sink, but Explode.js was only capable of generating 125 exploits. So out of these 125 exploits, only 46 were confirmed to enable malicious actions. So what I mean by this is that these 46 exploits actually triggered behavior that was not originally intended by the original package logic. Out of these 46, 2 had already been reported as vulnerabilities, and we responsibly disclosed the remaining ones. And to this date, this has resulted in 3 CVEs and 1 GitHub security advisory. So, in summary, we actually propose Explode.js, a novel tool for automatic exploit generation, targeting Node.js packages that can generate complex test drivers, even when the vulnerable function is not directly exposed by the module. It scales efficiently even in the presence of many imported packages, and that is able to compute non-trivial payloads tailored to specific sensitive sync context. In terms of results, as I've just said, it generated exploits for 46% of the ground truth datasets. That's 300% more than FAST and also 500% more than Node.js. Beyond the benchmarks, it was able to discover 44 previously unknown vulnerabilities with 3 CVEs and 1 GitHub security advisory, having already been assigned as the result of our disclosures. So finally, if you're interested in the deeper technical details, I encourage you to check out our paper. In the paper, I actually go beyond what I could cover here today and include the algorithm we use to compute the vulnerable interaction schemes, the formalization of the lazy value semantics, a brief catalog of the exploit attack patterns that we support, a more detailed evaluation, including the performance benchmarks, and also a candid discussion of limitations and avenues for future work. Thank you all for listening.
Any question? You should go to the mic. I don't know if it's a question or if people are... Yes.
Hello, Konstantinos Kalas from UCLA. Very cool work. I wanted to ask, could you give us some example of an interesting and more complex attack pattern?
I could give you one right now, but it's a very brief example. When you consider, for example, code injection, you could have, or at least something that we found experimentally, is something, for instance, you have an object, and then you do a property access. Right? You do a dot, or a member expression, you have a member expression, you have a dot, and then nothing else. So you actually have to complete this type of expressions. Right, so we could write an attack pattern, something that says you actually have to have a syntactic construct that makes this first expression valid, and then you could sequence actually an attack.
I see.
Something like
and also for this, for the attack patterns, you have to, the user has to also specify how to verify that that there was successful exploit in the end for its pattern, right? Or
I guess not really, because it depends. So Explode.js actually first detects the type of vulnerability, right? So you write an attack pattern. For instance, the one I said was for code injection, but actually Explode.js detects the type of vulnerability in the code, and when the exploit runs, what is intended is to verify the side effect of the vulnerability that it detected. So if it was code injection, what we expect is also as command injection that a file is created on the file system. So you have to write the attack pattern such that the payload does what it's expected to do, right? So
thank you.
It's a bit hard-coded that.
Oh, cool. Okay. You mentioned that there's 4 classes of vulnerabilities that your tool is able to detect. Do you have some insight as to like how this compares to all the vulnerabilities out there? Like, is this representative? Are there like large classes of things that this doesn't work with? Or
I mean, these were the ones that mostly focused on the detection part. So we had previous work in PLDI last year that focused on detecting this type of 4 vulnerabilities, which we found to be the most representative ones on Node.js. Right, so we focus on those. We could do maybe for redos and support some other type of vulnerabilities, but it was hard enough already for this one. So, sure. Yeah, thank you so much for the question.
Maybe I have one more question. So you reported 44 bugs you found, but then 4 CVEs. Is it because multiple are the 3 CVEs and 1 notice? Is it because some of them were redundant? Is it some of those bugs were redundant? Why is the mismatch between?
Sorry to interrupt, but actually some like package maintainers and developers, they said, okay, we acknowledge this is an issue, but we don't actually expect that people use our library this way. And so we're not going to actually say this is a vulnerability unless you give us an example of a package that actually uses this in a way that could be exploited. So they essentially don't believe it is something that is exploitable.
Let's thank our speaker again. Yeah.